Welcome. Today, we're diving into the world of processors, the heart of every computer system. I'm A. Sindhu Devi from Jerusalem College of Engineering, here to guide you through Unit 4. Let's explore how processors work, why they matter, and what makes them tick. Let's get started. Let's start with the basics, instruction execution. This is how a computer's brain, the CPU, follows the commands in a program. It happens through a repeating sequence called the instruction cycle. First, the CPU fetches the instruction from memory. Then, it decodes what that instruction means. Finally, it executes the command. This cycle is the heartbeat of every operation your computer performs. Understanding it helps us see how software turns into action. Let's break down the instruction cycle, the core process that keeps a computer running. First, the CPU fetches the next instruction from memory, guided by the program counter, and stores it in the instruction register. Next, the control unit decodes this instruction, figuring out exactly what needs to happen. Finally, the hardware executes the command, whether that's performing calculations, moving data, or updating memory. These three steps repeat continuously, powering everything your computer does. Let's look at the key parts inside a CPU that make everything tick. First, the program counter, or PC, keeps track of where we are in the instructions. It points to the next command to run. Then there's the control unit, the boss that directs traffic and tells other parts what to do. Finally, the arithmetic logic unit, or ALU, handles all the math and logic, the calculations and decisions that power the process. These three work together to keep the CPU running smoothly. Let's start by looking at the basic instruction cycle, the fundamental process that drives how a computer executes commands. At its core, this cycle repeats over and over, fetching an instruction from memory, decoding what it means, then executing it. It's a simple loop, but it's the heartbeat of every program running on your machine. Understanding this cycle gives us a foundation to explore more complex computer operations. Let's take a closer look at the basic instruction cycle when an interrupt occurs. Normally, the CPU fetches, decodes, and executes instructions in a steady loop. But an interrupt breaks in, it signals the processor to pause what it's doing and handle something urgent. This cycle shifts gears, saving the current state, addressing the interrupt, then resuming normal execution. Understanding this flow is key to grasping how computers respond quickly to unexpected events. Let's break down how a processor handles instructions step by step. First, in the instruction fetch cycle, the processor grabs the instruction from the memory address held in the program counter and stores it in the instruction register. Next comes the decode cycle. Here, the processor reads the instruction's opcode to figure out what needs to be done. Finally, during the execution cycle, the processor carries out the operation, which might mean fetching data, doing calculations, or storing results. Meanwhile, the program counter moves ahead, ready for the next instruction. MIPS instructions fall into three main groups. First, we have memory reference instructions, like load word and store word, which handle data moving between memory and registers. Next, arithmetic logical instructions, add, subtract, and/or, and set less than perform calculations and comparisons. Finally, branch instructions, branch equal and jump, control the flow of the program. This subset doesn't cover every integer instruction, and it leaves out floating point operations. But the core ideas behind building the data path and control logic come from these basics, and the rest follows similar patterns. When we implement any instruction, the first two steps are always the same. Step 1 is fetching the instruction itself. We send the program counter, which holds the address of the instruction, to memory, then grab the instruction from there. Step 2 is fetching the operands. This means reading one or two registers, depending on the instruction. For example, a load word instruction only needs one register, but most others require two. These steps set the stage for everything that follows. Now, let's look at what's left to do to complete an instruction. It really depends on the type of instruction we're dealing with. Whether it's memory reference, arithmetic logical, or branches, the steps are mostly the same. This consistency isn't a coincidence, it's by design. The MIPS instruction set keeps things simple and regular, making it easier to implement. Because many instruction classes share similar execution steps, the whole process becomes more streamlined and efficient. Let's look at how different instruction classes use the arithmetic logical unit, or ALU. Almost all instructions, except jumps, rely on the ALU after reading registers. Memory reference instructions use it to calculate addresses. Arithmetic logical instructions perform their operations there. Branches use the ALU to compare values, but what happens next varies. Memory instructions access memory to load or store data. Arithmetic and load instructions write results back to registers. Branches might change the next instruction address or just move on to the next one. Here, we see a block diagram of a MIPS processor implementation. It lays out the main functional units, like the arithmetic logic unit, registers, memory, and control components. The lines connecting them show how data and instructions flow through the system. This diagram helps us understand how each part works together to execute instructions efficiently, giving us a clear picture of the processor's internal organization. Here, we see data flowing into a unit from two different sources. Take the program counter, for example. Its value might come from one of two adders. Or consider the register file, which can receive data either from the ALU or from memory. Even the ALU's second input has options. It can come from a register or directly from the instruction's immediate field. Choosing the right source is the job of a multiplexer. It picks from multiple inputs, guided by control lines that are set based on the instruction being executed. This selection process is key to how the system operates. Now, let's dive into the basic implementation of MIPS using control signals. This is where the processor's control unit steps in. It directs the flow of data and operations based on the instruction type. Control signals act like switches, turning on or off different parts of the processor to execute instructions correctly. Understanding this foundation helps us see how complex commands break down into simple, coordinated steps inside the CPU. Here, we see the control unit playing a key role. It takes the instruction as input and generates control signals for the functional units and two multiplexers. Meanwhile, the third multiplexer decides whether to update the program counter with PC+4 or the branch destination address. This decision hinges on the 0 output from the ALU, which checks the condition for a branch equal instruction. It's how the processor knows when to jump or keep going. Let's walk through how instructions move through a processor step by step. First, the program counter points to the instruction's address in memory, fetching it. Then, the instruction itself tells us which registers we need. Once we have those register values, they're used in different ways, maybe to calculate a memory address, perform arithmetic, or check a condition for branching. Arithmetic results go back into registers. Loads and stores use the ALU to find memory locations, moving data between memory and registers. Branches use the ALU to decide where to jump next. This flow keeps the processor running smoothly. Let's talk about building a data path. This is how information flows through a system, from where it's created, to where it's processed, and finally to where it's stored or used. Getting this path right is crucial. It ensures data moves efficiently, without bottlenecks or errors. A well-designed data path supports faster decisions and smoother operations. We'll explore the key steps to create one that works seamlessly. Let's take a closer look at the MIPS implementation and its data path elements. These include key components like instruction and data memories, the register file, the ALU, and adders, all working together inside the processor. The figure highlights how the instruction memory, program counter, and an adder combine to create a data path that fetches instructions and updates the program counter. This update points to the next instruction, keeping the processor running smoothly and sequentially. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about how the instruction memory works in a processor. It stores the program's instructions and outputs the instruction at the address given by the program counter. The program counter, or PC, points to the current instruction and updates every clock cycle. To move to the next instruction, and adder increments the PC by 4. Since the instruction memory only reads data, it doesn't need a read control signal. Similarly, the PC doesn't need a write control signal because it updates automatically each cycle. The adder constantly adds its two 32-bit inputs and outputs the result. Let's talk about arithmetic logic instructions, or R-type instructions. These read values from two registers, perform an operation in the ALU, then write the result back to a register. Common examples include add, subtract, and/or, and set less than. For instance, the instruction OR T1, T2, T3 takes the values in T2 and T3, does a logical OR, and stores the result in T1. All these registers live in the register file, a set of 32 general-purpose registers that hold the computer's current state. Here, we see a multi-port register file with 2 read ports and 1 write port, alongside the ALU section. This setup supports R-format instructions, which use 3 register operands, 2 for the sources and 1 for the destination. It's a crucial design that lets us fetch 2 inputs simultaneously while writing the result back efficiently. This slide helps us understand how data flows through the processor during these instructions. When we read data from the register file, we have to tell it which register number to look at. Writing data is a bit different. We need to specify both the register number to write to and the actual data to store there. The register file always outputs the contents of the registers selected by the read inputs, but writing only happens when the write control signal is active at the clock edge. Because writes are edge-triggered, we can read and write the same register in one cycle, reading old data first, then updating it for the next cycle. The register numbers use 5 bits, letting us choose from 32 registers, while data inputs and outputs are 32 bits wide. Let's take a closer look at the MIPS load word and store word instructions. They follow a simple pattern, LW or SW, followed by a data register, an offset value, and a base register. The key idea is how the memory address is calculated, by adding the base register to the signed offset. For store instructions, we read the value from the data register to write it to memory. For load instructions, we do the opposite. We read from memory and write that value back into the data register. This process relies on both the register file and the ALU working together. We're working with 2 different sizes here, a 16-bit offset and a 32-bit base register. To combine these, we need a sign extend unit. This unit takes the smaller 16-bit value and extends it to a full 32-bit sign number, so it matches the base register size for proper addition. Alongside this, we have a data memory unit. This memory handles both reading and writing, controlled by specific signals. It also takes an address input and the data we want to write. Together, these components let us access and modify memory efficiently. Now, let's look at the data memory and sign extension unit. This part handles how data is stored and retrieved in memory, making sure everything lines up correctly. It also deals with sign extension. That's how smaller pieces of data are expanded to fit larger spaces without losing their meaning. Together, these functions keep data accurate and ready for the next step in processing. Sign extension means copying the highest bit, the sign bit of a smaller data item into the extra high-order bits of a larger destination. This keeps the value sign intact when we increase its size. Because of this, we need 2 extra units beyond the register file and ALU, the data memory unit, which handles loads and stores, and the sign extension unit, which does the bit replication for us. These work together to keep data accurate across varying sizes. Let's talk about the BEC instruction. It has 3 parts, 2 registers that we compare for equality, and a 16-bit offset. This offset helps us figure out where to jump next, relative to the current instruction's address. The key is that the branch target address isn't just the offset added to the current instruction, but to the address of the instruction right after it, that's PC plus 4. This detail is crucial for making branch instructions work correctly in the data path. Let's break down how the branch target address is calculated. The offset field is shifted left by 2 bits, turning it into a word offset. This shift effectively multiplies the range by 4. So the branch target address equals the current program counter plus 4, plus this shifted offset. But there's more. We also need to compare two operands. If they're equal, the branch is taken, and the PC updates to the target address. If not, the PC just moves to the next instruction. So the branch data path does two things. It calculates the target address and compares register values. Now let's talk about how we compute the branch target address. When a program needs to jump somewhere else in the code, it has to figure out exactly where to go. This calculation combines the current position with an offset, which tells us how far to jump. Getting this right is crucial. It ensures the program flows correctly, following the intended path without missing a beat or going off track. It's a small step with a big impact. Let's take a closer look at the part of the data path that manages branches. This segment is crucial because it decides where the processor should jump next, based on certain conditions. It handles the logic for choosing between continuing sequentially or branching to a new instruction address. Understanding this structure helps us see how decisions are made quickly and efficiently within the processor, keeping everything running smoothly. Let's break down how the branch target address is computed. We use a sign extension unit, a shifter, and an adder to get the correct address. To check if two values are equal, we send them through the ALU, performing a subtraction. If the ALU's 0 signal is on, the values match. For jump instructions, we replace part of the program counter with bits from the instruction, shifted and padded. And remember, MIPS uses delayed branches. The instruction right after the branch always runs before the jump happens. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Now, let's bring everything together by combining the data path components for each instruction class into a single, unified data path. This simplest design tries to run every instruction in just one clock cycle. Because of that, no resource can be used twice in the same instruction, so anything needed more than once has to be duplicated. That's why we have separate memories for instructions and data, and why functional units are duplicated. To share elements between instruction types, we use multiplexers controlled by signals to select the right input. This is how we create a single, complete data path. Let's look at how to build a data path that handles both memory reference and arithmetic logical instructions. We'll use just one register file and a single ALU for both. This approach keeps things simple and efficient. To make it work, we'll add multiplexers where needed, directing data flow depending on the instruction type. This example shows how to balance hardware reuse with the flexibility required to execute different operations smoothly. To build a data path using just one register file and one ALU, we need to handle multiple data sources carefully. Specifically, the second input to the ALU must come from two possible places. At the same time, the data we write back into the register file can also come from two different sources. To manage this, we place one multiplexer at the ALU's second input and another at the register file's data input. This setup lets us switch smoothly between sources, keeping the data path efficient and streamlined. Now, let's bring together the data path for both memory instructions and R-type instructions. Combining these paths means we can handle a wider range of operations with a unified design. This step is crucial for building a more efficient processor, where different instruction types share common hardware components. By integrating these data paths, we reduce complexity and improve performance, setting the stage for the next level of processor design. Let's break down how to build a simple data path for the core MIPS architecture. We start by adding the data path for instruction fetch. That's how the processor grabs the next instruction. Then, we include the data path for R-type and memory instructions, which handle arithmetic and data access. Finally, we add the data path for branches, allowing the program to make decisions. Together, these parts form the complete data path, as shown in the figure. In this part of the design, we focus on a core set of instructions. We're working with load word and store word. That's how data moves in and out of memory. Then, branch equal, which lets us make decisions. We've got the basic arithmetic and logic operations, add, subtract, and set on less than. Plus, we'll include a jump instruction to change the flow. This keeps the control unit focused but powerful enough to handle key tasks. Let's take a closer look at the MIPS ALU. Specifically, the 6 key combinations of its 4 control inputs. These control signals tell the ALU exactly what operation to perform. Understanding these combinations is crucial because they form the foundation for how the ALU processes instructions. In other words, this slide sets the stage for how the ALU interprets commands and executes the right calculations. Depending on the instruction type, the ALU needs to perform one of 5 key functions. For load and store instructions, it calculates the memory address using addition. For R-type instructions, it handles operations like AND, OR, subtract, add, or set on less than. When dealing with branch equal, the ALU performs a subtraction. We control these operations using a combination of a 4-bit ALU control input and a 2-bit ALU OP, which guides the ALU's behavior precisely. Now, let's focus on the ALUIP field. This small but powerful part of the instruction tells the arithmetic logic unit what kind of operation to perform. It acts like a command code, guiding the ALU to add, subtract, or execute other logical functions. Understanding this field is key because it directly influences how data is processed and manipulated inside the processor. So, the ALUIP field is where instructions start to take shape into actual calculations. This table breaks down how we determine the ALU control signals. We start with the 2-bit ALUOP input, which gives us a general idea of the operation. Then, the 6-bit function code refines that further, specifying exactly what the ALU should do. Together, these inputs guide the ALU to perform the right arithmetic or logic operation. It's a clear way to map control signals to the processor's instruction set. Here, we're looking at a method that uses multiple levels of decoding. The big advantage: it helps shrink the size of the main control unit, making the whole system more compact. Plus, by using several smaller control units instead of one big one, we can potentially boost the speed of the control unit. So, it's about efficiency and performance, breaking down a complex task into manageable parts that work faster and smarter together. Once we've built the truth table, the next step is optimization. From there, it's ready to be implemented using logic gates. This table shows how the 4-bit ALU control signals are determined. They depend on 2 key inputs, the 6-bit function fields and the 2-bit ALUIP field. Understanding this relationship helps us design the control logic that drives the ALU's operations efficiently. Before we dive deeper into the control design, it helps to take a step back and review the 3 main instruction formats. These are the R-type, branch, and load store instructions. Each one has a unique structure that guides how the control unit interprets and processes commands. Understanding these formats is key. They form the foundation for how we design the main control unit itself. Let's take a closer look at what makes each format distinct. Let's break down R format instructions. The opcode is always 0 here. These instructions use 3 registers, 2 sources, called RS and RT, and 1 destination, ARD. The function field, or funct, tells us which ALU operation to perform. We covered that earlier. Then there's the shamped field, which only comes into play for shift operations. This format keeps things organized, letting us specify exactly what the processor should do with each register. Let's break down how load and store instructions work. We start with a base register, called RS, which we add to a 16-bit address field. That sum gives us the exact memory address we want to access. For load instructions, the value from memory goes into the destination register, RT. For store instructions, it's the other way around. The value in RT gets saved into memory. This format keeps things clear and consistent when moving data between registers and memory. Let's break down how the branch equal instruction works. The opcode is 4, which tells us this is a branch operation. We compare 2 source registers, RS and RT, checking if they hold the same value. If they do, we calculate the target address by taking the 16-bit address field, extending it, shifting it, and then adding it to the program counter plus 4. This gives us the exact spot to jump to if the branch condition is met. Let's break down some key parts of this instruction format. Bits 31 through 26 make up the operation code, or opcode, which tells us what operation to perform. We call this field op5 through 0. Then, bits 25 to 21 and 20 to 16 specify two important registers, RS and RT. For load and store instructions, bits 25 to 21 always give us the base register, RS. Finally, bits 15 through 0 hold a 16-bit offset used in branch equal, load, and store instructions. These details are crucial for understanding how the instruction works. When we look at where the destination register lives, it depends on the instruction type. For load instructions, it's in bit positions 20 through 16. For R-type instructions, it's in bits 15 through 11. Because of this, we need a multiplexer to decide which part of the instruction to use. Adding this multiplexer, along with instruction labels and control signals, helps us manage the right register input in the data path. Each multiplexer has two inputs, so it only needs one control line to switch between them. Here, we see the core control signals that guide the data path's operation. There are 7 single-bit lines, each telling a specific part what to do, things like selecting the register destination, enabling writes, or choosing between memory and ALU inputs. Alongside these, there's a 2-bit ALU operation signal, which directs the ALU's function. Together, these control lines work with multiplexers to steer data flow precisely through the processor. This setup is what makes the data path flexible and responsive to different instructions. This table breaks down the role of single-bit control lines. Each line acts like a simple switch, turning specific functions on or off. Though they carry just one bit of information, their impact is crucial. They control key operations within the system. Understanding these lines helps us see how complex processes are managed through straightforward, precise commands. It's a small detail with big influence. Let's break down how these 9 control signals work. 7 of them are single-bit lines, and then there are 2 ALU operation bits. Together, they guide the processor's actions. These signals are set based on 6 input bits from the instruction's opcode, specifically bits 31 to 26. The diagram below shows how the data path connects with the control unit, illustrating how these control signals flow through the system. This is key to understanding how instructions get executed step by step. Let's take a look at a simple data path paired with a control unit. This setup shows how data moves through a system, guided step by control signals. The data path handles the actual data processing, while the control unit directs the flow, telling each part when to act. Together, they form the backbone of how instructions get executed in a processor, making sure everything happens in the right order and at the right time. Let's break down how the control unit works in this system. It starts by taking a 6-bit opcode from the instruction as input. From there, it generates several control signals. 3 of these signals control multiplexers, deciding things like which register destination to use, where the ALU gets its input, and whether data comes from memory or the ALU. Then, we have signals managing reads and writes in both the register file and memory. There's also a branch signal, which, combined with the ALU's 0 output through an AND gate, helps decide if the program counter should jump to a new address. Finally, a 2-bit ALU operation signal guides the ALU's function. Together, these signals coordinate the processor's actions step by step. This table lays out the control signals for each opcode value. For every instruction, it tells us whether a specific control signal should be set to 0, 1, or if it doesn't matter, marked as a don't care. This helps us understand how the processor directs data and operations based on the instruction it's executing. It's a key part of how the control unit manages the flow within the CPU. Let's break down how R format instructions work. For these instructions, like add, sub, and OR and SLT, the source registers are RS and RT, and the destination is ARD. This setup determines how the ALU SRC and Reg DSD signals are configured. R-type instructions always write to a register but don't access data memory. the program counter simply moves to the next instruction, so the branch signal is off. The ALUOP is set to 10, telling the ALU to use the funced field for control. We'll see how this compares to load and store instructions next. Let's break down how memory access and register control work in this part of the process. Memread and memwrite signals handle the actual reading and writing in memory. At the same time, regDSD and regwrite are set up so the result ends up stored in the RT register. For branch instructions, the RS and RT registers go to the ALU, which uses a subtract operation to check if they're equal. One key detail, when regwrite is 0, the memto-reg signal doesn't matter because no data is being written back. In those cases, we mark these control signals as don't care to simplify the design. Let's walk through how the data path works for an R-type instruction, using the example add instruction here. It all happens in one clock cycle, but we can break it down into clear steps. First, we fetch the instruction and update the program counter. Next, we read the data from two registers, in this case, T2 and T3, and set the control signals. Then, the ALU uses the function code to perform the addition. Finally, the result is written back into the destination register, T1. Let's take a closer look at how the data path works when executing an R-type instruction. This is where the processor performs operations like addition or logical functions directly on registers. The data path routes the instruction through the register file, the ALU, and back to the registers, all in a carefully coordinated flow. Understanding this process helps us see how the CPU carries out complex tasks step by step, with precision and speed. Let's take a closer look at how the data path works when executing a load instruction. This process involves fetching the instruction, decoding it, calculating the memory address, and then accessing the data from memory. Each step flows into the next, moving data through registers and buses until the value is finally loaded into the target register. Understanding this sequence helps us see how the processor handles memory operations efficiently and accurately. Let's walk through how the data path handles a load word instruction. We start by fetching the instruction and bumping the program counter forward. Next, we read the base address from register T2. Then, the ALU adds that base to the sign extended offset from the instruction, giving us the effective memory address. Using this address, we access data memory and retrieve the value. Finally, we write that value back into the register file, specifically into register T1, as indicated by the instruction bits. It's a clear, step-by-step flow. Load and store instructions work in much the same way, but with some key differences. For store instructions, the memory controls signals a write instead of a read. The data to be stored comes from the second register, not from memory. And unlike load instructions, there's no need to write data back from memory into the register file. These subtle changes define how data moves between registers and memory in each case. Let's take a closer look at the data path for the branch on equal instruction. This part of the processor decides whether two values are the same, and if they are, it changes the flow of the program. It compares the registers, checks for equality, and then updates the program counter to jump to a new address. This lets the processor make decisions and repeat tasks efficiently, a key part of how programs control their own execution. Let's walk through how the data path handles a branch on equal instruction. We start by fetching the instruction and bumping the program counter. Next, we read the two registers involved, in this case, T1 and T2. The ALU then subtracts one register from the other, using the function code for subtraction. Meanwhile, we calculate the branch target address by adding the offset to PC plus 4. Finally, if the ALU result is 0, meaning the registers are equal, we update the PC to the branch address. Otherwise, we keep going sequentially. Let's talk about how the control function is precisely defined. It all starts with the opcode. That's the 6-bit field in the instruction, bits 31 through 26. These bits act as the input to the control function. From there, we generate control lines as outputs. By using the opcode's binary encoding, we can build a truth table that maps each opcode to the correct control signals. This approach lets us finalize the control logic in a clear, systematic way. Let's talk about how the jump instruction works. Unlike branches, jumps aren't conditional, they always happen. The address for a jump is built by combining 3 parts. First, we take the upper 4 bits from the program counter, but from the instruction after the jump, so PC plus 4. Then, we add the 26 bits from the instruction's immediate field. Finally, we tack on 2 0 bits at the end. Put together, this forms the full 32-bit address that the program counter jumps to. Here, we see how the data path handles a jump instruction. To support this, an extra multiplexer is added to choose the new program counter value. It can select from the incremented PC, the branch target, or the jump target address. Along with this, a new control signal called jump is introduced. This signal activates only when the instruction is a jump, specifically when the opcode equals 2. This addition ensures the processor knows exactly where to jump next. Let's take a closer look at the data path for a jump instruction. This part of the processor handles where to go next when the program needs to jump to a new address. It's all about updating the program counter with the right target location, bypassing the usual sequential flow. Understanding this helps us see how the processor changes direction quickly and efficiently, keeping the program running smoothly. Single-cycle design sounds simple, but it comes with big drawbacks. The clock cycle has to match the longest instruction path, which means every instruction waits for the slowest one. This makes the clock cycle longer than necessary, dragging down overall performance. For complex instructions or floating point units, the penalty is even worse. It doesn't speed up the common, simple cases, which goes against the key idea of optimizing for the usual workload. That's why single-cycle implementations aren't the best choice. We've looked at the different cycles involved in the instruction cycle: fetch, decode, and execute. Now, these cycles for multiple instructions can actually happen at the same time. This technique is called instruction pipelining. To make it work, we break down instruction processing into 4 stages: fetch, decode, execute, and store. By overlapping these stages, we cut down the total time it takes to run several instructions, from 16 time units to just 7. This is the power of pipelining. Let's dive into the concept of 4-stage instruction pipelining. This technique breaks down the process of executing instructions into 4 distinct steps, allowing multiple instructions to be processed simultaneously. By doing this, we improve efficiency and speed, because while one instruction is being decoded, another can be fetched, and yet another can be executed. It's like an assembly line. Each stage handles a part of the task, keeping everything moving smoothly and quickly. In this instruction pipelining, we have 4 instructions moving through the process at once. That means we need 4 separate hardware units, each designed to work on its own task without getting in each other's way. These units operate simultaneously, keeping everything flowing smoothly. To make sure information passes cleanly from one stage to the next, buffers are used, acting like little holding areas that keep data organized and ready for the next step. Let's break down the 6 stages in this pipeline. First, we fetch the instruction. That means reading the next command into a buffer, ready to go. Next, we decode it, figuring out what operation to perform and what data we need. Then, we calculate the operand's addresses, so we know exactly where to find the data. After that, we fetch the operands from memory. Once we have everything, we execute the instruction, performing the operation and preparing the result. Finally, we write the result back into memory. This step-by-step flow keeps things moving efficiently. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about pipelined processors and their performance. Ideally, a pipeline with n stages completes 1 instruction every clock cycle. That means the processing rate is n times faster than doing things sequentially. So the ideal speed-up factor is simply n, but here's the catch. This ideal only happens if every stage finishes its task exactly on time, every time. In reality, interruptions and delays happen, so the pipeline can't always run smoothly without breaks. Now, think about this. What speed-up would you expect in a pipeline with n stages, and why? Let's walk through the pipeline stages in MIPS instructions. First, we fetch the instruction from memory. That's where it all begins. Next, we read the registers while decoding the instruction. Thanks to the regular MIPS format, reading and decoding happen at the same time, which speeds things up. Then, we execute the operation or calculate an address. After that, we access an operand in data memory. Finally, we write the result back into a register. Each stage flows smoothly into the next, keeping the pipeline moving efficiently. Let's look at how the MIPS instruction set is built with pipelining in mind. First, every instruction is the same length. This makes fetching and decoding much simpler and faster. Next, there are just a few instruction formats, and key fields always appear in the same place. This lets the processor read registers while figuring out the instruction type. Also, memory access only happens with loads and stores, so address calculation and memory access fit neatly into separate pipeline stages. Finally, aligned operands mean data moves smoothly in one step. It's a smart design for pipelined execution. Let's talk about how pipelining speeds up instruction processing. With a well-designed pipeline, we can complete one instruction every clock cycle. That's 4 times faster than doing things sequentially. The more stages in the pipeline, the bigger the potential speed boost. But here's the catch. This ideal flow only works if nothing interrupts the pipeline. In reality, delays happen. Sometimes, a stage can't finish its task on time. These interruptions are what we call pipeline hazards. Let's look at a situation where an operation takes 3 cycles to finish, from cycle 4 through 6. During cycles 5 and 6, the data in buffer B2 has to stay unchanged until the execution stage wraps up. Because of this, stage 2 can't move forward, and stage 1 is blocked too, since buffer B1 can't be overwritten. This causes the decode and fetch steps for the next instruction to be delayed, as the figure illustrates. Here, we see the instruction pipeline experiencing a stall for 2 clock cycles, specifically, cycles 5 and 6. After that, normal operation picks back up in cycle 7. Any situation that forces the pipeline to pause like this is known as a hazard. Hazards interrupt the smooth flow of instructions, and understanding them is key to improving performance. Let's talk about the 3 main types of hazards that can slow down a pipeline. First, structural hazards happen when there just aren't enough resources to handle overlapping operations, no matter how you try to schedule them. Next, data hazards occur when an instruction depends on the result of a previous one that hasn't finished yet. Finally, control hazards show up when the pipeline deals with branches or instructions that change the program counter. The simplest fix: stalling the pipeline to let things catch up. Let's talk about what really affects the performance of a pipelined processor. It all comes down to the functional units, whether they're pipelined themselves, and if there are enough of them to handle every possible instruction combination. When the pipeline has to pause because 2 instructions need the same resource at once, that's what we call a structural hazard. These hazards create stalls that slow everything down, and understanding them is key to designing faster processors. Let's talk about structural hazards. They happen when 2 instructions need the same hardware resource at once. A classic example is memory access. One instruction might be storing a result, while another is fetching an operand or instruction. If both instructions share the same cache, only one can go through, and the other has to wait. To prevent this delay, many processors use separate caches for instructions and data, allowing both to proceed without conflict. Let's talk about data hazards, a common challenge in pipelined processing. When an instruction needs data that isn't ready yet, the pipeline has to pause, causing a stall. Imagine 2 instructions running one after the other. The first updates a value, and the second depends on that updated value. If the second instruction runs before the first finishes, it might use old data, leading to errors. This is exactly what we call a data hazard. It's a subtle but critical issue in making pipelines work correctly. When we perform these 2 operations one after the other, in the right order, we get the correct result, 30. But if we try to run them at the same time, the second operation uses the original value, 10, instead of the updated one. This happens because the data for the second instruction depends on the first. This kind of problem is called a data hazard. To avoid mistakes, we need to execute dependent instructions in order, one after the other. Let's talk about the instruction fetch unit. Its job is to keep the execution units busy by supplying a steady flow of instructions. But this flow isn't always smooth. When the pipeline stalls, maybe because of a cache miss or a branch instruction, we hit what's called an instruction hazard. These hazards can slow things down even more than data hazards, making them a critical challenge to manage in processor design. Let's look at what happens during unconditional branching in a two-stage pipeline. Here, instruction I2 is a branch, and its target is instruction IK. At clock cycle 3, we fetch I3 while decoding I2 and calculating the branch target. But I3 was fetched incorrectly, so in cycle 4, we discard it and fetch IK instead. This causes the pipeline to stall for one cycle, leaving the execution unit idle. It's a small delay, but an important one to understand. Let's take a look at how branching impacts two-stage pipelining. When a branch occurs, the pipeline can't always predict the next instruction correctly. This causes delays, or stalls, because the processor has to wait until it knows the right path to follow. These stalls reduce the overall efficiency of the pipeline. Understanding this effect helps us design better strategies to minimize delays and keep the pipeline flowing smoothly. We've looked at the branch penalty, the time lost when the processor has to handle a branch instruction. It tends to be higher with complex instructions and longer pipelines. But there's a way to cut that penalty down. By calculating the branch address earlier in the pipeline, we can keep things moving more smoothly. This insight helps us design fast.
Thank you for watching. Please do like, share and subscribe my channel for more videos.